Hi, my name is George Cadman, and today I'll be giving a presentation on stress. To understand what's happening inside a material, we use a concept that we used to use in statics, the method of sections. We imagine slicing the body at any point that we're interested in finding the internal force, and this exposes an internal resultant force. We now use equations of motion and sum of forces, and we add up all the forces, and it must be equal and opposite to the external force. What's important to note is that this internal force isn't acting at a single point, it's distributed over the entire cut area. Stress is simply the internal force divided by the area it's spread over. Think of it like a pressure. It tells us how concentrated the force is inside the material. And we use standard units like pascals. There are two types of stress: normal and tensile. The normal stress is represented by the Greek letter sigma, and this happens when the internal force acts perpendicular to our imaginary cut plane. If the force pushes the material together, it's called a compressive force, and you can see this on the left in the diagram. And when the force pulls the material apart, we call it tensile stress. The other fundamental type is shear stress, represented by a tau. This happens when the force acts parallel to the cut surface. So now we're going to talk about determining the signs of stress, as it can be a little complicated. As you can see, stress here is represented by a sigma, and we have our coordinate plane with x coming towards us as positive, y to the right is positive, and z up is positive. We'll start by looking at this sigma right here, sigma xx. The first sigma describes which plane the force is acting on, and the second subscript describes the direction of the stress. So for example, sigma xx goes from the x side surface and points in the x direction. You can see this in sigma xy here, as the force vector is on the x plane but pointing in the y direction. When talking about positive or negative, if the stress is on a positive surface and pointing in the positive direction, it's a positive stress, and vice versa. For example, we can look here at sigma zx. So it's on the z surface, which is the positive direction, and it's pointing in the positive x direction, and therefore positive. If this was on the z direction but pointing the opposite way, it would be a negative stress. So far, we've simplified stress as force per area, but in reality, the stress at a single point inside a material is more complex. Imagine a tiny cube at that point. The force on the x face is different from the force on the y face and also on the z face. To capture this complete picture, we use what's called the stress tensor. It's a 3x3 matrix vector, and it is able to give you the exact force vector, the traction vector, acting on that plane. The diagonal elements are the familiar normal stresses, and the non-diagonal elements are the shear stresses. As you can see, it's a symmetric matrix, and for example, tau xy equals tau yx. So really, you only look at 6 parts of the matrix. But let's focus on the traction vector for a second. Imagine you take a cut inside a material. The traction vector is the actual force per unit area that one side of the cut exerts on the other. It's a single vector with its own magnitude and direction. But we can break it into the two previous stress vectors that we know: normal stress and shear stress. And then we can find it by projecting t onto the normal vector n. Using these two formulas on the screen, we're able to calculate both those different types of stresses. So why do we go through all the trouble to calculate the stress? Because it's how we predict if something will fail. Every material has a known strength, and that's based on the makeup of the material. As engineers, it's our job to design the part where the calculated stress is less than the actual strength of the material, and therefore it won't break. So for an aerospace example, when you have a rocket nozzle, there's a high pressure in the combustion chamber that creates a stress on the nozzle wall. And we have to design the actual physical strength of the nozzle to not break under these pressures. But at the same time, we're trying to minimize the width of the wall as to reduce the weight and therefore the needed thrust of the rocket. So now we're going to give a little example problem. So here we have a circular steel rod with a diameter, and we have a tensile force at the end. And we're going to calculate the normal stress in the rod. So we're going to start by cutting the rod down the middle, and we're left with one force on the right side. Then using sum of forces, well, let's start with, let's look at the area at the end of the rod. The radius is going to be 0.01 meters, and that means we have an area of 0.003 meters squared. We then know that the internal cut will have to equal the external force. So therefore, we're going to use the formula that stress equals force divided by area. Plugging in our numbers, we get a stress of 159 megapascals. Thank you so much for joining me for my presentation.